Yep. So our next speaker, taking us into lunch, is Clifford, who's a private researcher. Clifford develops open source software as the author and maintainer of Yosys, an open source Verilog synthesis and formal verification framework. And the title of his presentation is Open Source Tools for Formal Verification of Verilog HDL, YosysSMTBMC, and SymbiYosys. Okay.
Thank you. Yeah, I'm talking about a couple of open source tools that I wrote that can be used for formal verification, as well as some other stuff. But first, I'd like to talk about this, about the availability of tools of different flavors for people like students, hobbyists, and enthusiasts. Because when you're looking into fields like FPGA synthesis or HDL simulation, then it's quite easy to get your hands on tools and to learn how to use this stuff. So you can either download the tools from the commercial vendors that are offered for free and just install them and start playing around with them on the same day. But when you look into formal verification, then there is practically nothing that is available, either free to use or even open source. And in many cases, even when you're at the university, it's really hard to get access to formal verification tools through your university if you're not really working on a research project, but instead just would like to educate yourself how to use this kind of stuff. And at the same time, people in the industry are always complaining that they can't find anyone who has experience and knowledge about formal verification. And so there's an argument to be had how the tools that I wrote and that I'm talking to about today, how they compare with the commercial tools. But I'm not even going into this argument right now, because my argument is that we need something, because otherwise there won't be anyone who can use the commercial tools. You don't have the experience with formal methods. And just as a thought experiment, just think if it would be as hard to get access to Python than it would be to have access to formal verification tools, how many Python programmers would be out there and would be available for hire. Okay, so the tools I'm talking about today are Yosys, YosysSMTBMC, and SymbiYosys. So Yosys is a framework for everything you can do with Verilog, essentially. So I wrote the Verilog 2005 front end, and from that I can do formal verification as well as synthesis for a couple of FPGA architectures. Most notably, probably the Lattice IS-40 FPGA architecture, because I went through the effort to reverse engineer the bitstream format for IS-40, so we could also implement a fully open source place and route tool. So there is an end-to-end open source implementation flow for that kind of FPGAs, and also ASIC synthesis. YosysSMTBMC then is another tool that can use output generated by Yosys and interface with SMT solvers to use SMT solvers for various kinds of formal methods, but most notably bounded model checks. And SymbiYosys finally is a more or less user-friendly front end. So it still has no UI or something like that, but it has a very easy to write configuration file format. And there are a couple of different flows you can actually implement with these tools with different engines in the back. And if you're using Yosys and YosysSMTBMC and some of the other tools directly, and you would like to switch from one engine to another, then you have to rewrite a lot of scripts and stuff like that. And SymbiYosys just takes all these things away from you, and you just specify what kind of engine you would like to use, and SymbiYosys knows how to do that. So right now with SymbiYosys, I can do bounded and unbounded verification of safety properties, so you can prove that no bad thing is going to happen even within a certain number of clock cycles or forever. I can generate test benches from cover statements, so you can either really see the traces that are necessary to reach a cover statement, or you can just use this to figure out how deep you need to go to reach all the cover statements in your design. For example, if you would like to figure out what bound is a good bound for proving your safety properties. I can do formal verification of liveness properties. And then there are two things here that are marked to be done. So the backend tools can do this already, but this user-friendly front-end SymbiYosys doesn't have any features yet built in for that. And one of it is formal equivalence checking, and the other one is reactive synthesis. So for those of you who don't know, reactive synthesis is essentially synthesizing a circuit from the safety properties you provided. And couple of applications for that, but I personally like this to evaluate my safety properties, because if I have a traditional test bench and then I synthesize a circuit from my safety properties and it doesn't pass my test benches, then this is a good indicator that my safety properties are not really sufficient to describe what my design should do. Okay, so this is one possible flow with SymbiYosys that's using this Yosys-SMTBMC tool to bridge with SMT solvers. And I start out with a Verilog design and assertions, either assertions baked into my design or maybe as part of a formal test bench, things like that. I pass this through Yosys and generate SMT code. And then I can put this SMT code into Yosys-SMTBMC. It will talk to an SMT solver and in the end produce first of all, a pass-fail information, and if the check failed, I will get a counterexample trace in a couple of different formats. So the most important ones are probably a VCD file, so you can just look at it in a waveform viewer, a Verilog test bench, and a constraint file that can be used as input to the same flow again. So here the idea is when you have a very, very complex proof that might run for an hour or longer, and then it returns a counterexample and you found a bug, then of course you first fix the bug. And before you rerun the entire proof, maybe you would just limit it to the same kind of scenario that it just found a bug in. So let's say it's a very deep proof and it ran for 100 cycles. Then you can just use the first 80 cycles or whatever from this constraint file and see if in that state space the solver will find another bug or the same bug again, and only after that succeeded, you just run the unconstrained proof again. I have also a couple of flows that involve Eiger-based model checkers. So Eiger is a file format for gate-level circuit descriptions that can be interested for hardware model checking. This is what this kind of flow looks like. So I start out with a design, go through Yosys, create an Eiger file that goes through the model checker, and if the check fails, it produces an Eiger witness. However, in this step here, there's quite some optimization going on. So in the Eiger witness, it will tell me something like flip-flop 25 has an initial value of 0, things like that. But I don't know really what flip-flop 25 is. And it might not necessarily one-to-one correspond to a flip-flop in the original design. But what I can do, I can create, from this Eiger witness, I can essentially create constraints. And then I can rerun the same proof using an SMT solver and the same SMT-lib code that I've showed you before. And now it's a quite simple proof because I already have all the constraints from the Eiger witness. And I will very quickly get a pass-fail information from the SMT solver, and I can use this to generate counterexamples like before. So code, people keep telling me I should put code on my slides. I never listen. So there's going to be much, much more code in the slides to come. This is a really simple hello world example. So I have a counter, and I initialize this counter to 0 here, and then when the reset signal is high, I also reset the counter to 0, and otherwise I increment it. And then I have some formal properties down there. Those of you who know system Verilog assertions pretty well will probably see that this is actually not a valid system Verilog assertion because it has no clock event. But Yosys understands it, and this way it fits on the slide. I assume that the counter never reaches 10. I have no idea why I can assume this in this case. That's always the problem with assumptions with formal proofs. But then I assert if the counter never reaches 10, it will never reach 15. And of course, we can look at this and argue about it, but we can also use a formal solver to check this. And in order to do this, I write the SymbiYosys configuration file where I just tell it what kind of formal proof I would like to run. proof in this case means it's an unbounded proof, but because I'm using SMTBMC, it will prove it using K induction, and that's why there is a depth. So, so I can specify the engine I would like to use, a little bit of Yosys script to read in the design and to process it to a point so that the tool can work with it. And then this is an optional section that tells you which files are used by that. The utility of this is that this will create a work directory, and in this work directory I will have all the source files used for the proof. So when I'm going to archive this source directory at the end, I will also know exactly what version of the source code I ran the proof on. Okay, so I can run this in my tools. Just say SymbiYosys -f just means force. It will remove the work directory that already exists, this file, and then it will create its work directory, set up the proof, run the proof, and then say done. And in this case, everything in less than a second, because I mean, this is a quite trivial example. Okay, so I have 3 slides about the kind of properties I support in Verilog code. So I support immediate, assertions, assumptions, and restrictions. I have only very, very limited support for concurrent properties, for concurrent assertions, stuff like that. So the safe thing to do is just to use immediate assertions and just build your own state machines to check your properties. I can also verify liveness properties. So I support this kind of statements for fairness and for liveness. However, I have to admit that I'm personally not that convinced that that unbounded fairness and liveness is such a useful technique for hardware model checking, because in most cases it's not enough to just say ultimately the design will reach the good state, because it could be possible that it gets hung up somewhere and then waits, for example, for a 64-bit counter to overflow. And when this happens, then it will continue running, and then it will still be alive, because this will ultimately happen. But when we actually implement this in hardware, we probably don't want to wait that long. So, but I support it for those who need it. So one thing that I find very useful in formal test benches is to have 3 variables. And of course, all primary inputs of the design are 3 variables, but in many cases, it's not so easy to route primary inputs to a checker module or wherever you need the 3 variables. So you can either use this syntax here, which is system Verilog syntax for variables that are free in every cycle, or 3 variables that are essentially latched in the first cycle of the design. However, there are also Yosys-specific non-standard extension, any sequence and any constants for 3 variables that can be used. Okay, so more code, as I promised. This is a more complex example. On the left side, we see the design, and then on the right side, we have the formal properties that come with that design. They're just part of the same module in this case here for simplicity reasons. And the design itself is a Fibonacci number generator. So you give it a number n as an input and start the core, and it will run for a couple of cycles and then output the nth Fibonacci number. And what we have here is formal properties. We have some assumptions that the core is used correctly. So deliberately, I've chosen a very convoluted interface for this core, so that there are some outside assumptions that we need. And if the user is not using the core correctly, then it can do whatever. Then we have a block here where we say when we are in the cycle where the core is done, then we assert just for some cases that the right Fibonacci number was the 3rd. So the 0th and the 1st Fibonacci number is 1, and then we have 2, 3, 5, 8. We create cover statements for 13 and 144. These are also Fibonacci numbers. And we say we would like to cover the case where we passed n equals 15, and then the done signal was high the next cycle. We also have some safety properties here. So we assume that the outside world is not infinitely keeping the core in the pause state. So it will go forward. And if this is the case, and we actually start the core at one time, then ultimately it will end up in the done state. So in order to prove all that, we need 3 different configuration files for SymbiYosys. The first one proves our safety properties in an unbound manner in this case. This specific design cannot be easily proven with K induction. So I'm using IC3 as a method here to perform an unbounded proof. Then this configuration file here can be used to prove all the liveness properties in the design. And then on the right side, this will check that all the cover statements in the design can be reached. I don't have a depth here, so it just figures out how many cycles it will need to reach all the cover statements in the design. Okay, more examples. So this is something that the commercial vendors, most of them call formal apps, that you don't need to write your assertions yourself, but instead there are certain things from the design that we can extract safety properties from. In this case, we have a parallel case statement. And with the parallel case statement, the circuit designer tells the synthesis tool that only one of those values here will equal the condition variables. And of course, a synthesis tool is free to use this and optimize on that. But there is no guarantee that the synthesis tool will do that. And this is a typical case where you might test a design for many, many hours or days in an FPGA, and you never see a problem because the FPGA tool in this specific case has chosen not to optimize on the case that this is parallel, but then you go into your ASIC flow and you synthesize with a different tool, and suddenly your design breaks because the synthesis tool was capable of performing an optimization based on this parallel case information. And with an additional statement in the Yosys script, I can make the tool automatically generate assertions for this. So in this design, there is an input called bug. And if bug is high, then it's possible that A equals C and B equals C. Otherwise, we only reach this block here when A and B are not equal. So when bug is low, there is no problem here. And this is just to illustrate that we don't only check if the parallel case condition holds. We also check if it so we only check if it's violated in a situation where we actually use its output. That's what I like to say. So, a few more examples. This is a very straightforward implementation of a memory with a transparent read port. And this is a more convoluted implementation of exactly the same thing, or so I claim. And when you do, especially when you do FPGA synthesis, quite often you have cases where you have to massage your HDL code that instantiates or infers memory. And then at the end, it infers the kind of memory you like, but you're not sure anymore if it's still the same thing. So you would like to prove equivalence for that. And in this case, we just create a very, very simple, not really formal test bench, just a top module that instances post implementation of the memory. All the inputs are driven from the same thing, and then we have a read data 1 and read data 2 output for the different read data ports. Additionally, we have a constraints file, and in this constraints file, we say that both memories in these 2 modules must be identical in the initial step. And then we assert in all further step that the memories still say the same, they don't diverge in their content, and that the read data value is the same. We can run this and actually prove that these memories are equivalent. So this is another example using memories. And in this case, we don't check the memory against the reference, we check the memory against an abstract model. But this memory here, it has a bug. So first of all, we see this is a quite large memory. So this is 4 gigabytes. So this needs an SMT solver that is capable of modeling arrays. We can't just map this to a gate level netlist. Then the two lowest address bit, they encode the memory bank that we are going into. And here's the typo. We only shift this address by 1, and we should shift it by 2 bits to actually get this right address. So this is the formal test bench we are using. I'm instantiating this memory. And then I have here a model, an abstract model that I use to verify this memory. And in this model, I have an address. This is the one memory address that I actually model, and it's an any const. So this is a constant value throughout the trace, throughout the simulation run, if you like. But it's up to the solver to come up with this address. And if there is only one address that's problematic in your memory, then the solver, of course, will find this address for us. Then we memorize if we have seen a write to this address, because until we have seen a write to this address, there is no guarantee what should be read back. And then this is the data that we remembered. And here in the first block, we just memorize the value written whenever there is a write. And in the second block here, we assert that when you read something back and it's read from this one address that we monitor, then we assert that it's the value that we would expect. And because this design has a bug, we will get a counter example and trace, and then can look at the trace and see what's going wrong. And here you see in the traces, all the memory addresses of memory used are actually included in the trace. So even though this is a very, very large memory, we can still get reasonable traces and argue about what the design is doing. Okay, multiple clock domains. So when you're a sane person and you would like to implement a counter, then you would probably do it like that. So you just increment your counter with every clock cycle. However, if you're not a sane person, or if you did a lot of electronics with TTL chips in the 80s, stuff like that, then you will probably implement a counter like that. So with each clock cycle, you just flip the least significant bit. And whenever the least significant bit has a negative edge, you flip the next bit, and so forth. And this is, of course, also a counter. But of course, usually with formal, this is very problematic, because not only do we have multiple clocks here, we have clocks that we generate in our design. But still, we would like to verify that these counters are equivalent. So that's the property we have here. And we can do that with SymbiYosys when we use the clock to FF logic command in the synthesis script, which essentially substitutes all flip-flops in the design with logic and flip-flops that are clocked by the implicit global clock, which should run faster than all real clocks in our design. And it will observe those clocks, and if it sees a clock edge in this global clock by oversampling it, it will implement the right behavior. So of course, this will not perform anything like static timing. So there are still other things to verify about this kind of counter. But if we are thinking about our design in the same terms that Verilog simulation would think about it, that clocks trigger events, instantaneous, stuff like that, then we can prove that these two counters are the same. And we can also model stuff like asynchronous set and resets here. So for example, the code here is a flip-flop with an asynchronous reset and an asynchronous set. But when you, for example, implement this with Xilinx 7 series synthesis tools, then you will get pretty much this circuit here. And the reason is that the flip-flop primitives in Xilinx FPGAs do not support synchronous set and asynchronous sets and asynchronous resets. They only support one of the two. So what the tool does, it generates one flip-flop with an asynchronous set and another flip-flop with an asynchronous reset. And then it implements a latch that remembers if the last asynchronous event was a set or a reset. And this latch output is then used to select here which flip-flop output is used, the one of the flip-flop with the asynchronous set or the one with the asynchronous reset. Of course, this is horrible, but what shall we do? The only thing we can do about it is make sure that at least it's correct. And again, I'm not going to talk about the static timing aspects and stuff like that here. But for the way simulation usually sees things with clock edges instantaneously, doing something in the design, I can verify that these two things are equivalent. Okay, so one thing I'm working on right now is Risk5 Formal, which is a framework for end-to-end formal verification of Risk5 processes against the ISA specification. And my main motivation for doing that is that I need a nice test case to demonstrate that these tools can actually do real-world complex problems and not just some toy problems like the ones I've just shown you on the previous slides. You can go on GitHub and educate yourself a little bit about Risk5 Formal if this is something that interests you, or talk to me directly. Everything you see in GitHub is 6 months old because there is an exclusive use deal with one of the Risk5 companies. Okay, future work for this kind of stuff. So I've said right now there is very limited support for system Verilog assertion properties. I'm going to extend this a little bit. It will still be far away from the whole system Verilog properties feature set that the standard describes. So the primary goal here is to define a useful common set between the things that Yosys can do and the things that most commercial tools can do, so that you don't need to write different properties or different formal test benches depending on what kind of tool you target. Another thing is improved support for X propagation. So within Yosys, I can actually do formal verification of things that involve X propagation, but this is not yet integrated with SymbiYosys, and it's not available with all solvers now. So this is something else that I'm working on it. And the last thing here on this list is better integration with the Verific library. So right now already, if you have a license of Verific, you can take Yosys and link it against Verific and then use their system Verilog frontend and HDL frontend. But even there, I only have very limited support of SVA properties and only very limited support of PSL properties. And this is something that I would like to extend in the future. And there will be some kind of commercial offers for SymbiYosys with Verific library, maybe also bundled with commercial solvers, stuff like that for those that are interested in this kind of stuff, as something that you can just license and install in-house. But one thing that we really want to provide here are then also cloud instances with the entire framework and toolchain installed that can be rented by the hour. So it's easy to get started with this and to try it and to gather some experience with formal verification. Okay, that's my talk.
Thank you. Are there any questions in the audience? Yep, we have a couple online as well. So.
Hi, I'm Dan Neville from ARM. You mentioned your liveness example there with a 64-bit counter.
Yeah.
I was wondering whether you were planning on adding any form of abstraction kind of hints to the tool.
Well, for some abstraction, so usually counter is typically example for an abstraction, and you can write your own abstraction and just make an if-def and then say this is a free variable, but we constrain it to always be greater than equal than its previous value, things like that. It would not be hard to add stuff like that automatically, to add scripts where you just say variable so-and-so is a counter and it rips out the actual increment logic and substitutes it with assertions, but it's not something that has been done right now.
Hi, Ian Singleton, Synopsys. Am I right in thinking from your slides that if you were to use this along with the Verific front-end parser, then it would support the full SVLRM and you would be able to write temporal properties in SVA?
That's the goal.
Okay.
The thing is, Verific, as soon as it comes to SVA properties and stuff like that. The netlisted output is not actually a netlist you can execute as it is. This is more like a netlist version of a parse tree.
Yep.
And there is still work to do on my side to integrate all that. So right now, only very simple properties are supported. Okay. But this is the big to-do item for the rest of the year for me to improve that.
Okay, thanks.
Got a busy year, I think.
Hi, Claire Dixon, University of Liverpool. It's a comment really from one of your introductory slides. So in our department, we use new SMV, Spin, Upal, and Prism, and I think you can get those for, I don't know exactly the licenses, but students can, I believe, download them.
Yeah, so new SMV specifically, I don't have experience with Spin, for example, I just know it exists. But I think those tools are all BDD based. So it's really, really hard to get them to argue about very, very large systems. So some of the systems where I can prove non-trivial properties have end inverter graphs of over 2 million nodes. And I know that with a BDD-based approach, this is just not possible.
It's just your opening slide said there weren't any that people could just download and use, and I believe students can.
I mean, the focus here, I hope it says it on the slide, but the focus here is verification of hardware designs. So when you have Verilog code or HDL code, there is one tool from the C-prover people that can be downloaded from free. And I think the part they wrote is open source, but they incorporated a commercial parser that cannot be downloaded. However, I was not able to prove any non-trivial properties with that. I always got very, very weird error messages from the parser. I tried to reduce that to a minimal example, but all I managed to do was converting the error message into a segfault, and that was the point where I stopped. And
I'm not familiar with it, but thank you.
Okay.
Hi, Don Murphy from ARM. In your memcheck example, one of your SymbiYosys options was expect fail. Can you explain what this is doing?
Yeah, the Unix return code of SymbiYosys is usually 0 when it passes and 1 when it's timeouts or fails. And with the expect statement, you can say, what kind of things you expect? And when you write presentation slides with an example that's supposed to fail, and then you have a make file for that, so you can go there and download all the examples and then run make in the make file. I don't want the make file to stop because this thing failed. So I tell it, expect it to fail, and then it will return 0.
Right. Thank you.
Thank you. No, one question online, so I'll just leave that out and we can break for lunch. It's comparison with another tool, Cliff. So what type of designs and assertions did you observe the SMT-based approach perform significantly better than bit blasting, for example, with IGA?
Well, I think the arithmetic stuff doesn't work that much better with the SMT-based approaches. There usually bit blasting also is very, very good. But the big problem is memories. So with Risk5 Formal, for example, we have one processor core that's very hard to reset properly if it doesn't have its instruction cache. So we don't care and we just model it with its instruction cache. We could never do that with the IGA-based approach where I would have to bit blast the entire memory. But with the SMT solvers, that works very well.
Okay, thank you. And so Risk5 is going to be the biggest application you've done today?
Right now, Risk5 Formal is the biggest application I know of. However, I'm always amazed when I'm at conferences. People approach me and tell me my entire research is based on your tool because suddenly I had a flow from end to end. And my idea was, how can we make this part better? But it's much harder to evaluate that if you don't have everything on the left and the right of this slice. So in most of those cases, they are using it as a synthesis flow. But I don't know what people are doing with that.
Okay.
So.
Do you know how big your user base is?
No.
No. Okay. That's a simple answer. Okay, you didn't refer to the marketing department for that. Okay, I think we're into lunch, so on that bombshell we'll go to lunch, and I think we're back here in about just over an hour. Thank you very much, Cliff. Thank you.